Okay, welcome back. In this second half, we're going to deal with interpolation and regridding, which for our purposes are really the same thing. So what is interpolation? Well, it's a technique that lets you estimate unknown values of a variable using known values of that variable. There are many reasons you might need to interpolate. For instance, you might want to estimate values of something like temperature or phytoplankton biomass more frequently in time and space, or time or space, than they were actually measured. Or perhaps the measurements that you do have aren't in the times or locations or grid that you want them to be on. So you have to interpolate to those times or locations of interest. Or maybe some data are missing, or there's a gap in the data because an instrument broke. So you might want to try to fill in that gap using interpolation. Now, the example I'm going to use is climatological monthly average high temperatures in Seattle. And this seasonal cycle here should look pretty familiar. Unfortunately, we're pretty solidly in this phase of the cycle at the moment. And these points that I've plotted here, they're on the 15th day of each month because they're monthly averages, which generally represent the middle of the month. So it turns out that these types of line plots we've been looking at for a number of weeks now, they actually represent a linear interpolation. So you've been seeing this already. In other words, what we've been telling Matplotlib to do when we draw these straight lines here is draw lines between known points to linearly interpolate between points. And you could use these straight lines to estimate the value of this function here on a day that doesn't have a data point. So for example, if you wanted the climatological temperature on November 1st, we just locate that day on the x-axis, find its corresponding value on the green segment here, which is between October 15th and November 15th. And there you go, that's linear interpolation. It really is as simple as that. But what if we wanted to instead have all of our data points on the 1st of each month instead of the 15th of each month? So in other words, I want to regrid the data to a grid of x values located each on the 1st of each month. Well, I've done that using linear interpolation here, and the result is this dashed green line. As you can see, the curve for most of the year, it looks pretty similar. It looks good. But there are some spots, like this August 15th point, where the interpolation is not very accurate. So this is something to keep in mind. When you interpolate, the result is a best estimate, but it sometimes comes with a loss in accuracy, especially for linear interpolation. But we still do it because we often have to. You just have to be aware that the resulting data should not be considered real measurements. And sometimes you're going to get misleading results like this or this over here. Okay, so this is how you interpolate between one-dimensional data using SciPy. And it's actually a two-step process. First, you have to call the function interp1d from the interpolate module that we loaded earlier, and you call it on your original x and y data arrays. Now, interp1d gives you a variable over here, which you can give any name, but interp func is a good idea because this is actually a function here. Now, in the second step, you call that function on your new set of x values, your new x coordinate. And that gives you your new interpolated y values. You actually reuse this function again and again if you want to interpolate your old y values to different sets of new x values here. Just in case you need it, here's the link to the website with the API reference documentation for interp1d. Okay, so this slide here just breaks down each of those components that I went through. Your original x and y values, they're both 1D arrays. And same with your new x values and the new y values that you get over here. Using the argument kind, you can specify what type of interpolation to use. Often we choose linear interpolation, but there are some other options over here that I'm going to talk about in more detail in a bit. You do have to be careful if any points on your new x coordinate, the one over here, are outside the range of your original known x values. Now, interp1d, in that case, is going to give you an error unless you actually specify bounds error equals false. And if you do that, if you have these out of bounds x values, you should also tell interp1d how to fill those in. You can choose a fill value of np.nan, which just says they're missing. Or you can also tell it to extrapolate, and we'll try to guess at what those out of bounds values are on the left side and the right side. And sometimes your x values are going to be arrays of daytime objects, such as before when I was interpolating Seattle temperatures from the 15th day to the first day of each month. And just like with the lin regress function, SciPy can't handle date times. So again, you have to import matplotlib.dates as mdates, and then enclose both your original x values and the new x values that you're interpolating to inside this function mdates.datenum. And that converts those date times into just numbers of days. The full code for this example with the Seattle temperatures to make this plot here, it's all in the accompanying Colab notebook, so you can check that out. Okay. So you've seen linear interpolation. That's shown in the schematic here, right? You're estimating the black point based on a straight line between the yellow and the green points. Pretty simple. There are other ways to interpolate, though. In 1D, the simplest option is actually nearest neighbor interpolation, which just uses the nearest value to the point of interest. So if you interpolate to a lot of points, you're going to get this sort of step function look. There's also quadratic and cubic interpolation, which fit respectively second or third order polynomial curves to the existing points. And you can see that points farther away start to influence your interpolation to this black point when you use this option. It's no longer just these adjacent yellow and green points. So all these options here are available in the interp1d function using that kind argument. The next thing we're going to be discussing is actually 2D interpolation. And for this, you can also use that nearest neighbor method. But a better option is usually 2D bilinear interpolation. And that's the equivalent of linear interpolation for 2 dimensions. Now, if your parameter field is smoothly varying and you want higher accuracy, biquadratic or bicubic interpolation is also an option. Okay. And here's why you'd want to use 2D interpolation. It's usually because you're interested in regridding your data or changing the grid that it's on. Often grids are in geographic space, so latitude and longitude. But this also applies to data in depth versus latitude, or depth versus time, or maybe time versus longitude, or really any other 2 dimensions. Well, the most common situation, though, is that your points are on an irregular grid, like this curved finer mesh here. And that's common because the Earth is a sphere, right? So the only way to make each grid cell on the Earth represent the same amount of area is to have an irregular grid like this. That means your coordinates will each be represented by a 2D array. So a 2D array of latitude and a 2D array of longitude, or something else if your coordinates are different. But this is troublesome because you can't create that pretty pseudo-color plot of irregular data using p-color mesh. You also can't make a filled contour plot using contour F. And you can't look up what data is at a certain latitude and longitude coordinate in an X-ray object using the dot cell indexing notation. So in fact, you can't really do a whole lot with data on an irregular grid. So we want to regrid those data to a regularly spaced grid, like this larger one over here, sort of the rectangle. And that can be represented by one-dimensional latitude and longitude coordinate arrays, or whatever coordinate you have. The difference here is that regular grids with these 1D coordinates, those are compatible with p-color mesh, contour F, and X-array selection by coordinate. I should mention one other situation that you might want to interpolate between grids for is when you're just switching between 2 different regular grids. Often the first grid is high resolution, and the second grid that you're putting the points on is lower resolution, or vice versa. And interpolation can do that too. I should say regridding can get kind of complicated. So if you're looking for more information, I'd suggest this climate data guide page on regridding, which I've linked over here. Okay, so you've seen what we're going to do conceptually. This is how you do 2D interpolation using SciPy. It's actually a 3-step process. But the first 2 steps aren't necessary if you already have the new grid that you want to put the points onto. But if you don't, you have to create that grid. And to do that, the first thing is to use NumPy's linspace function to create evenly spaced one-dimensional x and y coordinates from the start to the end values, each with a certain number of points. We've seen this function before. It's similar to a range or range. The second part of creating the new grid is using NumPy's mesh grid function, to mesh those new 1D and 1D X and Y coordinates together into 2D arrays, the X grid and the Y grid. And what that's doing is something really simple, right? It's just stacking copies of like your horizontal X coordinate array until it's the height of the Y coordinate, and then stacking copies of your vertical Y coordinate array until it's the width of your X coordinate. Okay, so you have these grids. And then finally, you can use the grid data function from SciPy's interpolate module to get your Z values of interest, like a parameter like temperature. And that will be on those new X and Y grid locations that you just created. The first argument you give grid data is a tuple. So it's in parentheses. And those are your original X and Y locations, which if they aren't already, they have to be flattened into a 1D array format. Sometimes they might be 2D. You can flatten them using dot flatten. And then you give the Z values, the parameter that you're regridding, temperature or whatever. And that also has to be flattened into a 1D array of the same length as X and Y. And then lastly, you give a tuple with the X and Y grids that you just created. There's also this option to specify the method of interpolation. We often use linear for bilinear interpolation, but the other options are nearest neighbor and cubic interpolation. Okay. At the bottom here is a link to the API references for both mesh grid and grid data. And there's some more options that you can specify if you want. So here's that whole process broken down and annotated. Sorry for the busy slide here. But in particular, I just want to highlight that syntax that I mentioned. Flattening the original X, Y, and Z values into a 1D array. You can do that using dot flatten, right? And this is a pretty common situation. You'll often get these as 2D arrays to start. Okay, feel free to pause the video on this final slide if you want to read some of these annotations. Otherwise, these are in the PDF version of the slides, which you can download and look back on as you write code. That's it for this lesson. We'll go over these topics more in class on Thursday using some real data. Hopefully that should make everything a little more clear. But thanks for watching, and I'll see you on Thursday.